Hallo Georg.
Hallo Wolfram.
So, deine Folien sieht man und man hört dich auch.
Sehr gut. Gut, dann geht's ja gleich los. Yeah, dear students, thank you for joining in. I hope you can hear me. So today I will give the lecture remotely. I'm not at ETH right now, but hopefully all that will work out fine. Okay, so the topic of today are operational amplifiers. And with Wolfram, you've already seen how they work internally. And today we want to have a look at what one does actually with operational amplifiers. So let's quickly recap the properties of an operational amplifier. The symbol you see here, I hope you can see my highlighting here. And so differential amplifier, op-amps have differential input stages. They have very high input resistances, up to teraohms. They have very high differential voltage gains. So the gain A can be up to 10 to the 7. A high common mode rejection ratio. Wolfram has explained all about that. And the amplifier stages are DC coupled. So this is good for slow signals. The amplifiers have a small output impedance, which means they can deliver large currents. And typical is 10 to 20 milliamps, but there are also power op-amps that can deliver up to amperes. Okay, now what makes the op-amps so powerful is that you can, in principle, have a generic amplifier like this one or this one. And then what the actual circuit does is determined by the components that you put around the operational amplifier. And so with the same amplifier, you can do many different tasks. And you put either capacitors, resistors in the right combination around them. And this actually determines what they do, if they amplify a signal, if they filter a signal, and so on. And today we want to have a look how that actually works. Okay, now in order to prepare what I would like to tell you, I'd like to reiterate the voltage divider. Until now, we have used the voltage divider with an input voltage and then ground here. And of course, if we can also connect just two voltages here. And the question is, what is then the output that we see? In order to calculate that, we have a look at the two currents that go through these two resistors. They have to be equal to each other. And then we see that the output voltage can be easily calculated, and it's simply a weighted average of the two inputs.
Steckt im Computer das Kabel drin, mein Handykabel.
Is there a question? Did you forget to unmute, to mute? Okay, thank you. Okay, if we write those resistances as conductances, so 1 over the resistance, G1 is, for example, 1 over R1, G2 is 1 over R2, then it's particularly easy to see that the output voltage is a weighted average of the input voltages, where the weights are given by the conductances of these resistors, which is, in a sense, logical. If this has a large conductance, so a small resistance, then this voltage is closely connected to this voltage, closer than, for example, this one, if this has a small conductance. Okay. Now, let's have a look at one particular situation where we use an operational amplifier. It's the inverting amplifier situation. So we have an input voltage here that goes through a resistor into the inverting input of our op-amp. And then from the output, we have a feedback also into the inverting input of the op-amp through a second resistor. And the positive input of the op-amp is connected to ground. Now, what I'd like to do as a really first step is to go through what happens if we now change this input signal from 0 to some voltage. So let's have a look at this table. It shows a time series. At the beginning, we start with input signal 0, output signal 0, and this difference voltage between the plus and the minus terminal is also 0. This is a stable configuration, nothing happens. And then at time equals 0, we abruptly change the input signal from 0 volts to 0.3 volts. So this means at this point here, we get 0.3 volts. And then we can already use the voltage divider we've just talked about. At this point in time, the output voltage is still 0. Well, we haven't given the op-amp any time to react. And then we can simply calculate that given the resistor values, R1 is 10 times smaller than R2. So the weight in the weighted average is 10 times larger. And for that reason, we get almost the 0.3 volts, like 9/10 of the 0.3 volts. Or actually 10/11 of the 0.3 volts as the input voltage here. And now with an op-amp that has 10 to the 5 amplification, having 0.27272 volts on the input means that the output wants to go to 27,272 volts. Of course, it cannot do that. The supply voltage of the op-amp is simply plus minus 15 volts, and it cannot exceed those voltages. But I mean, its output wants to go, and in fact, the negative input here is at a higher potential than the positive, so it wants to go to minus 27,000 volts. And so what it does is it takes a step towards that direction with the largest speed it can master. And the largest speed is given by the slew rate, Flankensteilheit in this case, in this example, it's 1 volt per microsecond. So 1 microsecond later, the output has gone to minus 1 volts. The input is still 0.3, and so we can calculate the voltage divider between these two, and we get 0.18 volts as the difference voltage here between the two terminals. Now this means that now the output wants to go to minus 18,000 volts, which still, of course, is much larger than it actually can do. And so it continues to go to negative voltages with the fastest speed it can do, which means that 1 microsecond later, at 2 microseconds, we are at minus 2 volts in the output. With this, we can again calculate the voltage difference that we see on the input here. And now it's about 0.09 and something, which means that still the output wants to go to minus 9,000 volt. But we slowly approach the new point of stability, the new steady state. And so let's have a look what happens at a time, not really at 3 microseconds, but at 2.9. Well, there the output, of course, has changed to minus 2.9 volts. And we can calculate the voltage divider, and we see, okay, we approach 0 here. But still, this small differential voltage on the inputs means that the output wants to go to minus 900 volts. Yeah, still too much. So we have to come closer to 3 microseconds. At well 2.99 seconds, the output has gone to 2.99 volts. Now the differential voltage here has decreased still more. But still, it's a lot. It wants to go to minus 90 volts. Okay, so 1 more step towards 3 milliseconds, and we see that finally the output voltage has become so small, or so close to 3 volts, that this differential voltage becomes really, really small. With this differential voltage, the output wants to go to 9 volts. This is actually something it could achieve given the supply voltages, but it's still not its point of its steady state. So we have to go a small fraction in time further until this differential voltage has decreased well to 0.0003 volts. Now this, together with the gain factor, gives us an output voltage that is given by this value, which then in the voltage divider exactly calculates to this value. So this is where the op-amp is stable now. So we see we need a tiny difference voltage on these two terminals to generate a sizable output at the amplifier. And well, here you can see an example on how this looks with a real operational amplifier. So here, for example, you see a step in the input voltage to a positive voltage, and then the output voltage you see goes along an almost linear slope and finds a new steady state. And this amplifier, I took it from a data sheet, also has 1 microvolt per second slew rate. So you see this is a quite realistic scenario that the new voltage is approached in such a linear manner. Okay, now if we then, of course, going forward from 3 microseconds on, this state now is stable, and Wolfram has talked about what we have to fulfill in order to actually make it stable. And if it's not perfectly stable, then you can see that sometimes you get a small overshoot here on the output, and well, this is completely okay to have that, but if those overshoots get stronger, then it could lead to instability. Okay, now given, assuming that we have a stable setup, then this is the new steady state, and it will go on forever if we don't change the input voltage. Okay, so let's compute what happens as the steady state. So in order to do that, we have to look at this node at the inverting input, where we know that the current going through this resistor has to be equal to the current going into the amplifier plus the current going through the feedback. So this is what that equation says. Okay, now we can define the input resistance, which gives us a relation between the input current and the differential input voltage. And then we can identify those currents given by the voltage differences left and right of the respective resistors. And we can rewrite this equation in this way. Now we sort everything. We want to calculate the output voltage. So we put this on one side and have everything else on the other side. And then we use the gain, which connects the output voltage to the difference of the input voltage, and A here is the gain. Okay, using that, we can further simplify this and finally divide by R2 and find an expression for the output voltage, which is equal to the input voltage with a minus sign. It's an inverting amplifier, so we have to have a minus sign. And then a gain factor that depends on the amplifier gain, all the resistances in the system, but mostly on R2 and R1. And this is now if we take really large values of the amplification of our op-amp, then this simplifies to this simple expression here. So what this means is we get an output voltage that is equal to the input voltage inverted, scaled with the ratio of the two resistors in the system. And that's a very useful circuit to amplify signals. Now, we have seen in the first example that we need a really, really small input voltage difference in order to generate an output voltage. And well, this can easily be calculated, how large this input voltage difference has to be. So again, we use the formula for the gain. The output voltage is related to the difference input voltage times the gain. And then we can take the result we just calculated and replace the output voltage with this input voltage term and put all this in one side, as you see here. Then we identify this here as a parallel resistance. And we solve for the differential input voltage, and then we see that we come up with such an expression. Now, if you have resistors in parallel, sorry, the smallest one almost dominates. And we have here one resistor which is scaled with 1 over 1 plus A, and A is a large number. So this is very, very probably the smallest resistor. And so we can simply forget about the other two. And then we find a simple expression here for the input differential voltage as a function of the input voltage and the resistors in the system. And well, the important thing is that we have an amplification factor here in the denominator, which means that if we have a really large amplification, this difference voltage goes to 0. And that's actually one of the golden rules. You have already seen that we assume for a ideal op-amp that in a stable situation, this difference voltage is always 0. Okay, let's have a look at the output impedance. As we've seen at the beginning of the lecture, output impedance is an important concept. So it basically means how strongly does the output voltage depend on the current that we draw out of the op-amp. So if we have a large resistor here so the dotted line is everything inside our op-amp package. And if there is a large resistor here, then the output voltage would depend on how much current we draw out of it, because there would be a voltage drop over this. And now what we can do is we take this inverting amplifier again, and we put all the amplifier, everything until the load resistor into one package. And then we say, okay, we want to calculate what this combination of 3 resistors would look like if we replace it with an equivalent circuit where we have just one output internal resistance. Okay, and this is easily calculated. We have a look at the output node where we know that the current that actually comes out of the source from the amplifier has to be either the current that goes through the load or the current that goes back into the feedback. So this is what this equation says. Then we replace the currents as we always do with a voltage difference divided by the resistance for the internal resistance here, for the feedback. And then we find this expression. The delta UE, the difference output, difference input voltage, we calculate as we've done before using the voltage divider formula, and then we find one large formula here, which again, we assume that our amplification might not be infinite, but very large. And so we can simplify this simply by disregarding terms in the numerator that are not scaled with this large number. Okay, and then we find for our equivalent output resistance. So how do we get that? We have an expression for the output current as a function of the output voltage. This is this large thing here, or the simplification that we have here. So if we invert it and calculate the derivative, we find the expression for the equivalent resistor that would be in the equivalent circuit. And again, this is now a quantity that scales with 1 over the amplification and then some other components inside this. And as I said, this is a really large number. So the real output resistor that the op-amps have, this is on the order of maybe 100 ohms, but with an amplification of 10 to the 5, we find that the effective output resistance after this circuit is taken into account is like milliohms. So it's a tiny output resistance. A meter of a really thick cable has already several milliohms of output resistance. So this is negligible. So how does that work? That an amplifier which has 100 ohms real output resistance, this one here, appears as an amplifier which has almost zero output resistance. So I mean, in terms of performance of an amplifier, it appears like 100,000 times better. And the reason for that is that taking this signal at the output and comparing it to the input, well, which is called feedback, this makes everything better. So the amplifier measures what its output is, compares it to the input, and always corrects for all the disturbances that could happen in between. So feedback, Rückkopplung, is, well, helps to compensate imperfections. And one very common example are the outputs of benchtop power supplies, as you can see here. So there's a plus and a minus output, and then you have these sense connectors. And what the sense connectors do is they measure what the actual voltage is on the output. And now if you set your power supply to 9 volts, or in this case almost 10, and there would be something, for example, a long cable that causes a voltage drop, then the power supply can actually provide a larger voltage such that at the point where you measure the voltage, it is what you want it to be. And this is actually important in the work of Wolfram. When they supply the voltage to their detector and CERN, the power supply has to be far away, and the power supply actually has to measure what is the voltage that I deliver at the point where it counts and corrects for it. And there's a large loss because of the long power line. Okay, so we went through a bit of calculations in order to see what the characteristics of op-amps are. And of course, this now culminates into the 3 golden rules. So rule number 1 is that the input current is 0. So a large input resistance. This is simply given by the design of the amplifier. Then the open loop gain is infinite. And this is rule number 2. And actually a more useful rule which follows from that is that in a stable configuration, the difference of the 2 voltages on the plus and minus input is 0. And then the third rule is that the output impedance is 0, which means that the op-amp can deliver arbitrarily large currents to satisfy or to drive the voltage that it wants to drive. All of those conditions are not true for real op-amps. And if you now go to an electronic company, they offer maybe several thousand different op-amps. And basically, the art of choosing an op-amp is how close to an ideal amplifier you want to be in one or another property of the amplifier. And for some applications, it's more important to have a large amplification. And for some, it's more important to have a low input current. And for some, it's more important to have a large output current. And for that reason, there are many, many, many op-amps. What we want to do in this lecture now is basically treat op-amps as ideal amplifiers, and if you want to use them in a real circuit that is not too exotic, they will actually behave like an almost ideal amplifier. And now, if we use the golden rules to do the inverting amplifier again, it becomes really easy. The first thing you have to realize is because since this voltage difference is 0, and we know that the plus terminal is at ground potential, the minus terminal must also be at ground potential. And if you know that, it's completely trivial to calculate what must happen. We know that this current must be equal to that current. This current is now between voltage 1 and ground. So it's input voltage divided by R1. This current is output voltage with respect to ground. So it's output voltage divided by R2. These two have to be equal. Boom, we get the correct expression for the inverting amplifier. Okay, so using the 3 golden rules makes it much easier to treat op-amp circuits. And of course, one has to always know that using the golden rules makes an approximation. But in terms of op-amps, if you use an op-amp, it's really a very good approximation. So as we've seen, a typical amplification of an op-amp can be 100,000. And so the deviation that you get from ideal behavior typically scales as 1 over 100,000. And so if you don't care about the 5th digit after the comma, then you can simply assume that your op-amp is perfect. If you care about that, then you have to take care and go through the more complicated calculation. Okay, now let's quickly talk about a few different op-amp circuits. We've seen the inverting amplifier. Of course, there's a non-inverting amplifier, which illustrates an important concept. Now here, the input voltage is connected to the plus port of the op-amp. The output voltage is voltage divided with respect to ground, and the divided output voltage then is connected to the input. And this is a really important concept. So if you can, I mean, it's easy to divide a voltage. It's not easy to make it larger, but it's easy to divide it. And now if we have an amplifier that does whatever is necessary on its output to have these two equal, then we can, well, divide this down and for that reason amplify the output voltage. Yeah, it's like if you have a bank manager that always makes sure that 10% of your salary is equal to my salary, then you get 10 times more money than me all the time. And this is exactly what happens here. Yeah, so by dividing the output voltage down, by taking 10% of the output voltage and making sure that whatever comes out is equal to the input voltage, we amplify the output voltage by a factor 10. Okay, yeah, calculating that is really, really easy. It's just taking the output voltage times the voltage divider ratio and saying that that is equal to the input voltage, and then we turn that around and see that the output voltage is actually amplified. A special case of the non-inverting amplifier is the buffer, where we replace this resistor with a short circuit and this resistor with an infinite resistor. So we just remove it. And then you get simply output voltage equal to input voltage. And well, this circuit is actually used. It's really important because the current that goes into the amplifier here is negligible. Whereas on the output, it can drive an arbitrary current if it's an ideal amplifier, or at least a sizable current. And this means that we can decouple one part of our circuit from another part. And for that reason, buffers are really important. Okay, let's have a look at a slightly more complicated amplifier. But using the golden rules, it's also really easy to calculate what this here does. So here we have 4 resistors. And it's a differential amplifier. The most important rule is that the difference between these two terminals is 0. And this helps us to see that whatever the output of this R1, R2 voltage divider is, 1 times with the U minus input voltage and U out input voltage. Yeah, so this is 1 voltage divider. And what comes out of this voltage divider has to be equal to the other voltage divider where we have U plus and ground as input voltages. And so here you find the corresponding formulas. This is the U plus and ground voltage divider. This is the U minus and U out voltage divider. And if we sort all those terms and put U out on one side, you see that it's proportional to the difference between the two input voltages scaled with the ratio of these resistors as an additional gain factor. So that's really important circuit to well, basically calculate the difference between two voltages. Well, we can not only make the difference between the voltages, we can also add voltages. And this is another very common amplifier that uses actually up to an arbitrary number of inputs and adds all those voltages together. And how does it do that? Each voltage is converted to a current. One golden rule says there's no current going into the amplifier here. So all the current that is generated by those resistors. Different rule. We have ground on one terminal. So this terminal here also needs to be at ground potential. So the currents that each branch here has is always between this voltage and ground. So it's easy to calculate. It's just the voltage divided by the resistance in each branch. All those currents add together, and then they have to go through the feedback resistor here. So this point also is at ground. So what this voltage is it must be the voltage that makes the correct current flow through the feedback resistor. So in terms of formulas, we see that the current is the sum of all input currents. The feedback current is the sum of all input currents. The feedback current must be the output voltage divided by the feedback resistor. Okay, and this has to be negative. The sum of all voltages scaled with the same resistor here. Okay, so we get an output voltage which is again scaled with the ratio of resistors, very typical, and then times the sum of all input voltages. It actually doesn't matter that we get the inverse of the sum because of this minus sign. If this doesn't do what we want, we can always add another inverting amplifier after it in order to flip the sign. One important application of this amplifier is analog digital to analog converters. So what you want to do there is you want to convert a numerical number that is represented as digital values to an analog voltage. And if you scale the resistors here according to such that Ri is some R times 2 to the I, then each voltage here, you can switch the same voltage and you can generate current contributions that scale like the value in a binary code. And then if you add them together, so you can put a switch in front of each of those, then the switch position corresponds to your digital number, and the output voltage will then be an analog representation of that number. Okay, one more example of an op-amp circuit here is a transimpedance amplifier. So what it does, it converts current into a voltage. And that's really important to read out detectors. Many detectors produce a current that is proportional to whatever you want to detect. One example would be a photodiode that generates a current that is proportional to the light power that liberates charge carriers inside the diode. Now, these currents are typically very small, and so we need an amplifier to convert it into some convenient voltage that we can then use to do something else with, for example, to digitize this with an analog to digital converter. And as we've seen, this kind of feedback here produces an output voltage that is sufficient to generate a current in this feedback resistor, which is equal to the current that comes in. Yeah? For the adding amplifier, the current that came in was generated with, well, many resistors. And in this case, we do the same thing. We just generate the current with a different device, in this case, a photodiode. And then it's trivial to calculate the output voltage. It's simply the voltage needed to drive the same current as from the photodiode through the feedback resistor. So if you want this voltage to be large, you have to use a large feedback resistor, and values up to gigaohm can occur. And this kind of amplifier is known to be well, challenged with stability, especially if you use really large values in this feedback resistor. And for that reason, it's typically necessary to add a capacitor here. So what does this capacitor do? In order to make the circuit stable, an output voltage change must be felt here on the input. Now, if this resistor is huge, gigaohm, then well, you have to change the output voltage by a lot. But in order to make it stable, the effect of changing it can be transmitted, so the transient can be transmitted through a capacitor, such that the input already sees some change faster than through this large resistor. Now, this has the advantage that this is only to make the system stable for fast signals. But in the long term, the feedback capacitor has infinite resistance. So in the long term, what is important is the feedback resistor. So all the feedback capacitor does, it adds a low pass filter behavior to the whole system, and with that it makes it stable. So yeah, another way to say that is the feedback capacitor limits the bandwidth, and we can simply replace the feedback resistor here with the parallel circuit of a feedback resistor and the feedback capacitor, and we find this behavior here, which is a first order low pass filter. Yeah, so this simply reduces the gain at high frequencies by introducing here a term that scales with omega. Okay, one circuit that in a similar way was used in the project that you all started to calculate and lay out is the Howland current pump. And this is, well, the opposite. It converts a voltage to a current. So this is also really important. For example, if you want to drive a coil, then the physically relevant thing inside the coil is the current. This generates a magnetic field. And for example, through temperature, the resistance of the coil could change. And so it's good to have an amplifier that actually keeps the current constant, independent of what voltage is needed to drive that current. And so in order to see how this works, so there's 5 resistors here around an op-amp in a non-trivial way. So let me walk you through how to see how that works. Since there's no current disappearing into the amplifier at this point, the current 1 must be equal to the current 2. And since they have opposing directions, there is a minus sign. Now we can convert the currents to voltages directly using those formulas. And since the two resistances are equal, we can also just simply equate the voltages. Okay, now since the difference voltage here is 0, we know that voltage 2 so the difference between here and here, is equal to, where are we, voltage 4, the difference between here and here. And the voltage 1, difference between here and here, is equal to minus voltage 4, this one. So this is a consequence of that. Now we take the positive input here, and there we have three currents that are relevant. There's the current coming through the resistor on the plus side here. We have the current coming through this resistor, and we have actually the current that we're interested in, the load current that goes through the load resistor. Okay, now we can replace all those things in this formula, and then use the identities we have seen up to calculate an expression for voltage 3. Now we have to use one more time the golden rule that this voltage difference is 0, which lets us realize that the difference between U3 and U1, so the difference between this voltage and this voltage, is equal to the difference between the input voltages. So if this here is at the same potential, and we go up by 5 volts here and up by 3 volts there, then these two input voltages must be different by 2 volts. So the difference between these two must be equal to the difference between these two. Okay, so this we put here, and then we find that the output current, the load current, is simply equal to the difference between the input voltages scaled with RB, so the value of this and this resistor. And this is remarkable. All the other resistors in the system, so we require that this resistor is equal to that resistor, and the load resistor can be any value. As long as it's in the operational parameters of the op-amp, it will drive the correct current. And in our project, we use this in order to generate the current that goes through the photodiode, through the light emitting diode, LED. Okay, so yeah, it's a bit complicated to explain how it works. It's a good exercise to go through the math and do it for yourself, realize how all this works. But in the end, it's really satisfying to have a really simple expression that generates a current. Okay, so you see combinations of resistors and an op-amp can be combined in many different ways to produce different results. And one really good example is the INA 105. So it's one op-amp and 4 precision resistors in one package, as you can see here. And now simply by connecting the outputs of this chip in different ways, you can realize really different functions. So for example, you can add, subtract, invert, average, double, half, and many more things, and they are all described in the datasheet of the INA 105 that you can find here. And so it's fun to look through those and look through those and realize why it works, and quickly see with the golden rules that this actually does what is advertised. For example, this circuit here, you see that the output voltage is an average of the two input voltages. So how does it do that? Very simply, it uses the two input resistors to generate as a voltage divider, and then simply connects the output with nothing else to the inverting input. So this is just a buffer. Yeah. And like that, you can see many different circuits there. Okay. Now it's time for the break. So we will see each other in a quarter of an hour. Thank you. Okay, let's continue. Just seen someone has sent me a chat. I don't know how to look at that in presenting mode, so I will read that after the lecture. Okay, the next thing that we want to have a look at is the logarithm amplifier. And this is an example for amplifiers that realize a nonlinear function where the output voltage is some function of the input voltage. And this can be realized by a nonlinear element in the feedback circuit of the op-amp. So it works in 2 steps. In step 1, we convert the input voltage to a current. This is simply done by this resistor. And in the second step, we convert the output voltage to a current using a nonlinear bipolar junction transistor. And then the amplifier takes care to make these 2 currents equal, as we've seen already with the inverting amplifier. Now in this case here, we want an exponential dependence, and one way to realize that is with a transistor. So we use a simple transistor model for the collector current, and can then simply calculate that the input voltage is converted to or has this relation to the exponential of the base emitter voltage of the transistor. Okay, someone is not muted. Let me do that. Okay. Now the chat popped up. Good. Okay, and then, well, what the amplifier in the end does, it generates an output voltage. Okay, we have to invert now this relation using the logarithm to get the voltages independence of the currents. So those were the currents independence of the voltage. Then identify that the voltage that we have here is equal to the output voltage, and see that the output voltage then becomes a function of the input voltage, where the input voltage is in the logarithm here. Okay, and this is a typical behavior. If we put an element in the feedback branch of the amplifier, then we get the inverse of what that element does. Yeah, so this produces a exponential voltage current relation, and what we get is a logarithm. The same thing we have already seen also with the non-inverting amplifier, where in the feedback branch we had a voltage divider, so it reduces the voltage, and then this is fed back to the input. And so what the amplifier has to do is has to amplify the voltage in order to get equal inputs. And here we have kind of the same, that the amplifier has to generate a logarithm in order to get this exponential dependence equal to the input. Okay, the next thing we can do is exchange the position of the nonlinear element. So now if we put the nonlinear element in front of the amplifier and have a simple resistor in the feedback loop, then the 2 steps are reversed. We convert the input voltage to a current using the nonlinear transistor, and then convert the current to an output voltage using the linear, sorry, there's an R missing, R2 feedback transistor. And then, of course, we have the exact same math, except that we do not have to do this inversion and find an output voltage that now is a function of the exponential of the input voltage. Okay, and because this is an inverting amplifier, we have to take care of the minus signs. But as I said, this can always be corrected by adding one more inverting amplifier in the chain of amplifiers. Okay, really useful are these exponential and logarithm amplifiers in order to generate an analog multiplier, which is otherwise difficult to realize. So what you do here is you calculate the logarithm of one voltage and the logarithm of another voltage, add them together, and then calculate the exponent of that, which then, of course, due to this identity, gives you the two voltages multiplied. Okay. Yeah, now I want to come to one more really important amplifier circuit that is actually very commonly used and a bit less trivial than the first ones we've seen. So here you see 3 op-amps and a bunch of resistors in one package called an instrumentation amplifier. And what it does is it amplifies the difference between the two input voltages and gives an output voltage that is proportional to that. Now, this sounds a lot like an operational amplifier, but the instrumentation amplifier is actually designed to work with different input voltages, where you really want to subtract one voltage from another, want to measure the difference between two input voltages. And they can have a sizable difference. So it's for example used as the excuse me, the difference between, or as an input circuit for an instrument. That's why it's called instrumentation amplifier. Where, for example, you have a BNC connector on the front panel of your instrument, and you want the difference between the ground and the shield and the pin, the center potential of this coaxial cable, to be the input. Yeah, and there it's a good idea to have such an input amplifier. And then, of course, this input voltage can be many volts. Whereas if you would directly use an operational amplifier, then this input voltage can only be, microvolts. Otherwise, the operational amplifier would already saturate. So you need the resistors that you see in this schematic to somehow have the difference amplification in check, and also to have a precisely defined difference amplification. Another important feature is that instrumentation amplifiers have typically very high input impedances. So there's virtually no current flowing into the instrument if you use this as an input stage. This is also important for many detectors that cannot supply a large current, and the detector would just not work if you have an amplifier that requires a current delivered by the sensor or detector you want to read out. An interesting property is that the gain of the whole setup can be adjusted with a single resistor. So the differential gain is set by this one resistor. And typically the resistor is not part of the package. And you can put externally the resistor that corresponds to the gain that you want. Sometimes the operational amplifiers also have a set of resistors built inside, and you can simply, by connecting one of the pins to the resistor that you want, choose if it's a gain of 10, 100, or 1,000, and then those resistors are precisely matched to give you exactly that gain. Yeah, so they're commercially available, and they include 3 operational amplifiers and 6 position resistors in one package, and sometimes, as I said, even more resistors to give you a choice of gains for which you do not have to find the correct resistor. Okay, so let's have a look how this circuit works. And well, I must admit, this is not the most obvious op-amp circuit if you look at it the first time. And so let's divide this into 2 sections. And how do you do that? it's always a good idea to divide at the output of amplifiers, because what comes afterwards does actually not change the value of this output. As we've said, an operational amplifier can, or the ideal operational amplifier can deliver arbitrarily large currents. So if we put resistors here, if they are large or small, doesn't matter. The voltage generated by this output is given what comes before. Yeah, and so it's a good idea to have a look what this actually does. We name this voltage 1, voltage 2, and then what happens afterwards here, we have a look as a second step. So the first step, and actually this is also part of your project, is well, a combination of two op amps that are kind of crosswise connected to each other. And in order to understand what this system is doing, it's really important to use the rule that the potential at the two input terminals is the same. And I've already done this by identifying this is the input voltage, the minus input voltage. And since these two have the same potential, we find the minus input voltage also at this junction here. The same is true for the plus input voltage that you can see here. And because these two are the same, you find the plus input voltage also here. Okay, and then it's a simple voltage divider. What we divide is minus input voltage and output voltage 2, this intermediate output voltage 2. And the result of this voltage divider must be input voltage plus. Okay, so this is what's written here. The plus input voltage is equal to the corresponding voltage divider formula for the two resistances involved with the minus input voltage and voltage 2. Okay, and then it's simply arithmetic to solve that for voltage 2, and you see what we get is a copy of the plus input voltage, and then the difference between the two input voltages scaled with two resistors. Okay, now we can do the exact same thing mirrored for voltage 1, and we find this is a copy of voltage minus, and then subtracted also the difference between the two input voltages scaled by the same gain factor. So this gives us the two voltages here and here. And you see each of those gets a copy of the voltage to which it's closest, so to say, plus this scaled version of the difference voltage. And now you see if we make this gain resistor, if we make it small, then the scaling factor can be large. And we get, if we want, a large gain on this difference voltage. Okay, now what the part B of the circuit does, this is we have already seen, this is a difference amplifier. And so the output is simply the difference between voltage 2 and voltage 1. And so that's easy to calculate. What we get is 1 times the difference between the input voltages, because there was a copy of each input voltage in those. And then twice, because they have no different sign, the difference of this input voltage scaled with the gain resistors, with the gain factor. And well, putting this in a nicer form, you see that the output voltage is proportional to the difference of the input voltages with a gain factor that has, well, this 1 from the copies, and then this part which depends on the gain amplifier. So this means if we have this gain resistor infinite, then we simply, or if we don't put a resistor there, then we simply get a gain of 1, so just a copy of the difference of the input voltages. And if we put a small value here, there can be a large gain. And this is also a reason why these amplifiers are very versatile and easy to use. So you can choose from application to application what kind of gain you want. Okay, now let's move on to filters. And at the beginning of the lecture, we have, well, simply calculated the RC filter. And there's one more example here. So we have an AC input voltage that goes through the RC filter. And then after that, we put simply a buffer. Yeah, so the input signal is connected to the plus input, and the output is directly connected to the minus input. So this, what this operational amplifier does is it just generates a copy of the voltage here to here. And now, why this is useful, when we started to talk about filters, we have seen that the load, that if we want to combine different filters, that the load of one filter onto the one that comes before basically destroys how well the filter works. And we have seen filters that actually take many time constants to settle and so on. And now we can forget all that because the buffer prevents that this filter is any load on that filter. And this buffer prevents that this filter is any load on that filter. So this means we can combine an arbitrary number of filters, and we do not have to care about the values of the components, since the op-amps take care to deliver the necessary current. Yeah, we have seen before that if we make the resistance here much larger than this one, then this is not a significant load, and so on. But that this becomes really difficult if you want to combine a large number of filter stages. And so in principle, this is already the solution to have filters that have really a large number of stages and much more flexibility than simply an RC filter. So what we get here is one filter order. This we have already seen. A simple RC filter is a first order filter. And if we combine it with another RC, we get a second order filter. And if we combine it with a third, we get a third order filter. And between each order, we need one op-amp. Well, this is perfectly fine, but we can do better. And there are different filter topologies. And one really common one is the Sillen-Key topology that is shown here, this one. And well, this allows us to improve on that behavior still quite a bit. So let's have a look at node U1, this one here. Okay, the filter is simply a buffer. So we know that the output voltage, which is connected to this terminal through here, is kept at the same value as this plus terminal. Yeah, so this is what this says. And then we have a look at this terminal here. There are three currents involved: the current through resistor 1, the current through resistor 2, and the current through capacitor 1. And so let's simply write them down. The current through resistor 1 is given by the voltage difference between the two nodes, input voltage and voltage 1, divided by the value of the resistor. The current through the capacitor is given by the voltage difference between voltage 1 and the output voltage, scaled with the impedance of the capacitor. And the current through resistor 2 is, of course, the voltage difference across that resistor divided by the value of the resistor. Now, we have a look at this node here. We know there's no current going into the amplifier. So the current through resistor 2 has to be equal to the current going through capacitor 2. So that's what is written here. And using this expression, we can solve for voltage 1. And then we can replace voltage 1 in the first thing and arrive with this formula here. This we can still write a bit nicer by, first of all, multiplying with R1, and then bringing everything on one side, which is the input voltage, and everything else on the other side. And then what we're interested in is the transfer function of this filter. So we calculate A, the transfer, as the output voltage divided by the input voltage. So we have to go through all this and find this expression here. And this is already the final result. In order to make this a bit more easy to understand, we again have a look at a special case where the two resistances and the two capacitors are equal. And then we find that this is equal simply to the transfer function of a normal first order low pass filter squared. Okay, so this shows us that with this shell and key topology, now you can see there are actually two RC filters. There's a resistor and a capacitor, and a resistor and a capacitor. That we get two filter orders with one op-amp. Yeah. And that's about the best you can do. So if you want to construct a filter which has a higher order than 2, you would cascade more and more shell and key stages. Okay, now in order to see this simple expression here, we've chosen the components in a certain way, but it's not the only choice we have. We can choose them differently. In order to make the example easy, we choose the resistances equal, and we then find that this is a low-pass filter with a certain corner frequency given by this expression. And there's one more thing that we can choose. The ratio between the capacitors would not change the corner frequency, but it changed a different quantity, and that's called the quality factor. And the transfer function here depends also on that quality factor. So for example, if we make the two capacitors also equal, that's the situation we just seen. This is the second order filter. This gives us a quality factor of 0.5. And this is the lower curve here. So we stay here at small frequencies at gain 1 or 0 decibels amplification. And then we go down into this, and here we see this is the slope of the filter. Now this is not the best we can do. So the ideal filter is shown here as the black curve. It's the so-called brick wall filter that just stays at amplification 1 until the corner frequency and then drops to amplification 0. This is the ideal low-pass behavior. And we can come a little closer to that by choosing a different quality factor. As you can see here, if we choose quality factor 1 over square root of 2, then we stay longer, this orange curve, we stay longer at gain 1 and then go quicker into the slope where I mean all the filters are equal. Yeah, so this is the nicest turnover from gain 1 into this slope without actually going to a gain that is larger than 1. Yeah. We can push the quality factor higher, and then you see for a short frequency interval, the gain is a bit larger than 1, and then we even stronger, even steeper go into this slope where the filter then declines with its characteristic slope. And I mean, which of these situations is ideal for a certain application depends on what you want to do. And so if, for example, if you want your signal to be, I mean, kind of large as long as possible and then go very steep, then a high quality factor might be nice. If you want the signal in the pass band to be really, really smooth, then the 1 over square root of 2 quality factor might be better. Yeah, what you see in this graph also is a simulation of the transfer function of a shell and key topology using KiCad. And what you see here is that actually after it has suppressed the transfer a lot, it starts to get go up again at really high frequencies here at a megahertz. And the reason for that is this feedback capacitor here. You see, this feedback capacitor at really high frequencies becomes a short circuit. And the amplifier has a limited bandwidth. So, I mean, the amplifier will exactly do what is calculated here as long as it can. So, I mean, inside its operation parameters. And one limit of its operational parameters is the speed at which it can react. And now, if the input signal is so fast that the amplifier cannot react fast enough, then we deviate from the calculated behavior. And there's actually a part of the signal that flows through this capacitor to the output and is not affected by the op-amp at all. So this one has to take into account. If you really require an attenuation at really high frequencies, then a shell and key topology might not be the best, and there are different topologies that are better. Okay, now it's actually quite an art to pick the values of the resistors and capacitors in order to design the perfect filter. And in order to simplify that, there are many tools available. One tool that I like is the one from Analogue Devices. It's a company that produces operational amplifiers. And of course, their tool suggests always an Analogue Devices amplifier. But it's a really convenient way to generate filters. And so what you have to specify in order to generate a nice custom filter is a passband region. So here you say, okay, I want 0 decibels gain, so an amplification factor of 1. And I can allow up to 3 decibels deviation from that in the passband, which goes until 10 kilohertz. And then I have a stop band, which starts at 45 kilohertz, and there I want at least 50 decibels of reduction. So this is what you specify. And then the tool calculates a filter response. And here you can choose with a slider, basically, how much emphasis is given to certain optimization strategies. And one strategy is to go for the minimal number of components. And the minimal number of components, this is optimized in the Chebyshev design. And in this case, you need a third-order Chebyshev filter to achieve this filter behavior, which is within your design parameters. And this is then realized in 2 stages, because per op-amp, so one stage is one op-amp, per stage we can at most have a second-order filter. So in order to realize a third-order filter, you have to have 2 stages. Okay, but now it could be that you say, okay, this is not so nice that actually in my passband, the amplification changes by up to 3 decibels. And so we could go to a Butterworth filter, which is the one that's optimized for a maximally flat passband. So it keeps this amplification equals to 1 or 0 decibels for as long as possible, and it's as flat as possible, and then goes smoothly into the filter suppression slope here. And well, this is obviously nicer than that, but you need one more stage, one more filter order. Sorry, one more order. You need one more filter order, so it's a 4th order Butterworth filter in order to do that. But since you can realize 2 orders per stage, it stays at 2 stages. And this might be a good optimization strategy, that as long as you do not increase the number of stages that you need, your effort in equipping, for example, a board with those components doesn't significantly increase. And then you get a nicer filter performance basically for the same effort. Here is then what the tool generates as an output. So it gives you a schematic. Of course, it suggests analog devices, amplifiers, and it tells you which values of components you need in between. Then you can optimize here, for example, for low noise, and you can tell it what the voltage levels in your system are. And you basically get all the components chosen in the optimal way. If you now have a look at the time response, so this is a time plot of a signal that goes from 0 to 1 at time equals 0. And then, of course, you see that the filter takes some time, certain response time to react to that. And then it has a certain wiggling. This is also typical for filters. And the steeper the filter is, the more such ripples you will see. This is simply a fact that a steep function in the frequency domain, if you Fourier transform that, always produces something that is well, has ripples here in the time domain. But there's also a filter topology. If you say, okay, I cannot really deal with that. This is not the ideal behavior I want. For example, I need that this output signal is settles as quickly as possible. Then you could go for a Bessel filter. And so this is optimized for fast settling. And then you see that it becomes much quicker and stabilizes to the nice new value here in a much smaller time. But it might be that you need additional filter orders in order to achieve that. And in this case, it's now a 6th order Bessel filter. And so like that, you can see that you have to find a compromise between the perfect filter behavior and the effort you want to invest in electronic components to get the system doing what you want. Yeah, one last thing I'd like to mention is the bandpass filter. So if you combine a low-pass filter and a high-pass filter, you can cut out one section of frequency that can pass through the filter, and all other frequencies are suppressed. And the ideal behavior, again, is this black curve, where it's simply 0 everywhere except in this band of width delta f, and at the center frequency f0 around the value f0. And if you now tell the tool to generate such a filter, you can, for example, get a filter that is reasonably flat up here. It's reasonably steep. And in this case, it took 8 filter orders to get this filter calculated. And the more filter orders you invest, so to say, the closer you can come to this ideal filter. Now we can define a symbol for such a bandpass filter, simply specifying the basic shape of the spectral response, the center frequency, and the width of this band. Okay, now the bandpass filter will be an important component in discussing noise, Rauschen in electronic circuits. So there are different kinds of noise in electronic circuits, and here I've listed the 3 most common ones. Thermal noise, it's called Johnson-Nyquist noise, and sometimes one of the names is left out, or Wärmerauschen, thermisches Rauschen. And this is caused by the motion of charge carriers due to their thermal energy. And if you want to get rid of it, you have no chance but to cool your system. And for that reason, sometimes detectors are cooled to very low temperature in order to, well, just make the charge carriers inside move less. Then there's shot noise. It's also unavoidable. also called Poisson noise, Schottky noise, Schrotrauschen in German, is caused by the granularity of charge. Yeah, so if you move one electron at a time, that's the smallest steps you can make. And now these the electrons, for example, simply flowing in a cable, they arrive at statistically distributed times, and so they produce a current that is like granular and has a random component to it, and this is shot noise. And then there's 1/f noise, and in contrast to the first two examples, 1/f noise is mainly a technical noise. It's also called flicker noise, pink noise, rosa Rauschen, and it can be caused by different things, for example, crystal defects in semiconductors, or statistically varying conductivity. So if you have a material, for example, the gain boundaries in carbon resistors. So you have grains that are pressed together, and the current flows through the points where those grains connect. Then it can heat up, and then a different grain could have a better path. And so the current basically flickers around between different paths, and this produces noise. Or also the interaction with the environment, like temperature or acoustics. Some materials are change their conductivity depending on pressure. And so if you have a pressure wave coming from the outside, it can be that it changes the conductivity of your signal. Okay, now in electronics, we quantify noise in different ways. So if we have a noise series here, and we can draw a histogram of the values that we've measured, so this you can measure with your oscilloscope, then calculating the RMS value of this, so root mean square, or effective value, Effektivwert, is simply taking taking the square of the voltage values, and then calculating, well, the sum divided by the number, so this is the mean, and then you take the root. Yeah, so it's a root mean square. It's basically the same thing as calculating the standard deviation of this signal or the corresponding width of this curve. And well, that's a statistically valid way to specify the noise in a certain signal. Another very common way to specify the noise is the peak-peak amplitude. And by definition, this is simply the difference between the most positive and the most negative part of your signal. But that's, of course, statistically really bad, because it depends on how long you measure. It's completely random. And you see, if we would have stopped the time series a bit earlier, then this would not have been the most positive, but the one next to it. So the whole value that you calculate as the real peak voltage is simply based on 2 points, this one and this one, in your whole time series. And that's not the best way to characterize noise. But the peak voltage is, so to say, a measure of how much deviation do I actually expect to see. And in order to get an approximate value for that, it's common to use 6 times the RMS voltage. Yeah. So this corresponds to a 90, I think 99% area of this curve. And so if you don't look too long, you don't expect to see voltage values that are larger than this. And then you have a statistically sound way to define the peak voltage. And that's often used in specifications. Okay, now let's have a look at the connection between power and signal shape. And the 3 examples I've shown here, so it's white noise, sinusoidal signal, and the constant DC signal, they all have the same power. Yeah, so with the constant signal, of course, it's easy to calculate how much power this produces. You can just connect it to a resistor and measure how hot the resistor gets. With the sinusoidal signal, you can do the same. But of course, in order to generate the same power as this one, it has to be a bit larger in the peaks because in between it's smaller. Yeah, so just to compensate that, you need a larger value. And for the common 230 volts that we typically have, the peak voltage needs to be almost 100 volts higher. And then, of course, if you have a voltage signal, a noise signal, then you have to average all these peaks to see how much power that produces. Yeah, so in terms of efficiency, the DC signal is the most efficient to deliver power. As you can see, yeah, you need a higher amplitude to deliver the same power with the sinusoidal signal, and you need an even higher amplitude if it's a noise signal. If we have a look at the spectral distribution of the power, we see for the DC signal, all the power is concentrated at zero frequency. That's what it means to have a DC signal. For an oscillating signal, in this case, the 50 Hertz signal that we get from our main connectors, this, of course, has a frequency of 50 Hertz, so there's a peak at 50 Hertz in the power spectrum. And typically, the height of this peak, we give the effective value of this voltage. So this is 230 volts RMS effective value. And keep in mind that if you see that, it means that you have actually a signal going up to almost 100 volts higher than that and down to almost 100 volts lower than that. And then the noise spectrum, I said this is white noise. White noise means that all frequency components contribute with the same strength. And now if you would repeat this noise signal for many times and average the spectrum, this would really average to the line that you see in the background. And so there, all the power is distributed over a large number of frequencies in the spectrum. Okay, so let's formalize this a bit more. If we have a time-dependent signal and we want to know what power is transmitted by it, the easiest way to do that is convert it to power using a resistor and then measure the power. And well, in formulas, simply the power as a function of time is, of course, the voltage times the current. We can replace the current with the voltage divided by the resistor and get the voltage squared times 1 over the resistor. The power thus is, well, 1 over the resistor is the conductance times the voltage squared. Now, this relation is true for every moment in time, but it's often not useful to measure the power delivered every moment in time. So, I mean, if you use an electrical heater to heat your flat, you don't want to know that the power goes up to a certain value 100 times per second and then down to 0 again and up to a certain value. You want the average power that, I mean, makes your flat warm. And so what we're interested in is the average, the time average of the power. And of course, that's calculated by integrating over, we can integrate over this expression here, and then build the time average of that. And this is exactly the same math as we've seen with the RMS value. So we can define an integral version of our RMS voltage as well, the square root of the time average of the squares of the voltage. Yeah, okay, of course. With that, we find, simply putting this here, that the time average of the power is, of course, the conductance times the time average of the square of the voltages, which is exactly that. So we simply find that the time average of the power is equal to the conductance times the RMS voltage. And well, that's a fundamental relation, and it's basically why RMS voltages are important. They tell you how much power a certain signal conveys. So the RMS value can be determined by measuring the power. So you'd simply take the power, multiply with the resistance that you've used, and take the square root, and you find the RMS voltage. And that's actually used. There are some signals that have so high frequencies that you cannot digitize them nicely and calculate what the RMS value is. Well, of course, you can calculate this otherwise with a computer. And well, if you can do that, then a used method is actually to let the signal, well, convert the signal to power, to heat, and measure how much heat that is. Okay. Now I'd like to talk about power spectral density. If not all components of the spectrum contribute with the same amount to the power, then it's important to talk about how this is distributed in the spectrum. And even if they all contribute with the same amount, the power spectral density is a really useful feature. So it quantifies how frequent signal components at a frequency contribute to the power, and the defining equation is this one, that the power is equal to the spectral density integrated over all frequencies. And so consequently, the spectral density has to have units of watts per hertz. And now we can do an example, and let's use our bandpass filter we've just seen. So we take a signal with a constant power spectral density, and then we let it pass through a filter with a given filter bandwidth, and then we use a resistor to convert whatever comes through to power. And so let's take an example with 0.1 watts per hertz spectral density. We choose a filter with 20 hertz bandwidth. And then we use a 50 ohm resistor to convert that to power. And then, of course, we find the 0.1 times 20 equals 2 watts. That is transmitted through this filter here. And now if we have a filter with a larger bandwidth, then we linearly get, I mean, if we would use 40 hertz bandwidth, we get 4 watts of power transmitted. And in this case, actually, we don't need to know what the resistance is if we already know that the signal contains 0.1 watts per hertz. That's good enough. And there are situations where it's actually, it works like that. For example, in radio signals, you often calculate signals in terms of power. But there are also situations where you don't know a priori how much power would be flowing for a certain resistance. Or, I mean, or you would have to make an assumption about a resistor, which you don't want to make. And so is there a way to get away from power? I mean, like specify the same quantities without actually using the resistor? And yes, there is. So we can go in analogy to the power density, we can define an amplitude density. So let's take this, I mean, in order to connect the two examples, we need a resistor. We have seen how to calculate the RMS voltage that produces the 2 watts here. So we have to multiply the 2 watts with the 50 ohms. This is 100. And then take the square root. So we get 10 volts RMS. This is the voltage that with the 50 ohms generates the 2 watts in this part of the signal. Now, we can simply replace the power in this equation now with a scaled version of this RMS voltage. And then we say, okay, with the other part, we do the same. We scale with the conductance. And then we want a quantity that we can integrate over the frequency. And since it is an amplitude, it has to be squared. So we define the power spectral density, the amplitude spectral density rho simply by this equation. And then it's clear how to calculate it. If this is constant for every frequency, this is also constant. So if we integrate it over a certain range of frequencies and want it to be equal to a certain RMS voltage, then we have to integrate, square the value, integrate, and take the square root. By taking the square root, we also take the square root of the frequency interval. So what we have to do is calculate the square root of the frequency interval. And then from this voltage and this square root, we can calculate that the amplitude spectral density has to be 2.23 volts RMS per root hertz. Okay, so this is a strange quantity that has strange units, volts per root hertz, but it's very common to use it to specify noise levels in electronic systems. It's basically just a shorthand for saying, okay, we know that the relevant quantity are energies and powers. And I mean, they're relevant because there's energy conservation. There's no amplitude conservation in nature. And what we mean when we write this down is that the square of that one is a meaningful quantity, but this one has to be scaled with a conductance. And now we just leave away the conductance on each side, and we can write down the RMS value as the integral of the power spectral density. Okay. Yes, so these quantities are important because what's behind it is always a power that is transferred through a signal or a system, and in order to calculate how that is done, we need those quantities. Okay, that's it for today. Sorry for being late a little bit. And next lecture, we then will have a look at how to measure power spectral density. I will stay in the Zoom session a little longer in case there are questions.